Good morning, ladies and gentlemen. Did I say last? Last unit of the year we got going on here. Uh, Applications of definite integrals. First ones we're going to be looking here are integrals as net changes and linear motion revisited. So if we revisit this, it's basically pretty important to check out that S of t as I'm moving through here. S of t in calculus typically refers to as the position function, and also S prime of t is the same as v of t, which is the velocity function. And sometimes they may denote that as ds dt. They may be using differential notation for you to see the derivative. Just make sure you're on par that these two are the same thing, okay? And then we're also going to be looking at S double prime of t is the same as V prime of t, which is the same as A of t, which actually is acceleration. And as differentials, they might call it dv dt, which would stand for derivative of velocity with respect to time, or the second derivative of S with respect to t, which would be the second derivative of position. Okay, so just be aware of the different, notations they give you. They might use differentials. They may not use differentials. Okay, and as we are moving along here, okay, and to be quite honest, that's the one I was the least comfortable with when I was a student. But just know that if you're seeing like an exponent or something in derivatives, whatever that exponent is, that's the derivative that they're talking about, all right? And so if we know all of this notation above, it also follows, if we're thinking of derivative of position to get velocity, derivative of velocity to get acceleration, or the second derivative of position to get acceleration, it also follows that the antiderivative or the integral of A of t, or acceleration, actually gives me my velocity plus my constant of integration. Okay, so remember, this would be antiderivative, and that doesn't mean they don't like them, right? And just remember, this is going to accumulate. This accumulates velocity. Okay, so if I'm accumulating, actually there I'm accumulating acceleration, and in the bottom when I accumulate velocity to get position, okay, so I'm going to cross that out, and I'm accumulating acceleration to get velocity. And then if I accumulate velocity, I'm actually going to get technically position, okay? Now, also, it's important to know that this right here is going to show, they both show net change, okay? They both show net change. And this one also shows a net change. And in this case, down here, if I integrate velocity and I show a net change, that's going to show a net change, or it's going to show position, or it's going to show me displacement. And that's kind of what we're looking at today, is as we're cruising along, which one is it, which one am I looking at, okay? And then the very last one, so it will also follow that if I have the definite integral of absolute value of v of t, now remember that is talking about speed, okay? Speed is the absolute value of velocity. And if I integrate an absolute value of velocity, this is going to give me the total distance traveled from A to B, all right? And only with the absolute value does it show me total distance traveled, okay? Because if I integrate velocity without absolute value, what it does is it gives me a net displacement of the object from A to B, or it gives me the net displacement basically is the position or location, okay, from the starting point. Okay, so if I integrate the absolute value of velocity, it gives me total distance traveled, but if it's not the absolute value, basically what it's doing is it's showing me the position or location that object is to the right or to the left from where it started, okay? And let's just take a look at a couple things. You know, we looked at this before. Well, suppose the initial position of an object is 0 feet, okay? The graph of the velocity of the object in feet per minute, so here's my feet per minute on 0 to 5, so these must be minutes here. So 0 to 5 minutes is shown below. And as I'm looking at this thing, okay, if I want to know the total distance traveled, from A to B, okay, well, that's going to tell me how far did it move, the total distance it moved, including forward and back, okay? So if I'm looking at velocity, and I actually integrate, and I integrate this, and I'm taking, when I do that, I'm taking feet per minute times minutes. So this integral is actually going to give me feet, okay? So if I integrate velocity, it actually gives me position. And if I think about the total direction or the total distance traveled, well, think about this, the velocity graph. Well, if velocity is positive, I'm moving to the right. And if velocity is negative, I'm moving to the left. And if it's positive here, I'm moving to the right. But what is the total distance traveled? Well, I travel 8 to the right, plus I'm also traveling 3 to the left, plus another 5 to the right. Now, the total distance traveled, remember, that's forward and back summed up. My total distance traveled is going to be 16 feet. And what the total distance traveled is, that's basically the same as my integral from 0 to 5 of the absolute value of v of t dt. That's total distance traveled. And what we're trying to do is we're trying to get a feel of how do we find total distance and what is the displacement of the object. Okay, now displacement is basically all it is think of it as the distance you are from where you started. Its displacement is like the position where you are in relation to from where you started. Well, the displacement, well, if I move to the right, I went 8 to the right, plus now if I'm moving to the left, I went to the left. So I'm kind of thinking moving on the number line, like if I started at 0, I went 8, and then from 8, I went back 3 to the left, and now I'm going to be moving another 5 to the right. So where am I in relation to where I started? Well, it sure looks like I'm going to be at 10 feet, okay? So 10 feet. Well, that is the same as the integral from 0 to 5 of v of t dt without an absolute value, okay? So that's what we're really trying to look at, the difference between total distance, displacement, and now we're also going to be looking at position here, okay? What is the position of the object at t equals 5? Well, if I'm thinking about position, okay, I always need to remember my position will equal my initial position plus displacement. Okay? My position is my initial position plus displacement. My displacement is simply how far I moved in relation to where I started. So if I'm looking at this, and up here on the top, I believe it says an object, its initial position of an object is 0 feet. So if I want to know where this particular thing is, I'm going to take 0, my initial position, plus my 8, plus my -3 to the left, plus my 5. And because I started at 0, my position is going to be 10 feet. And if I wanted to show that as an integral, well, I'm going to show my initial position 0 plus my integral from 0 to 5 of v of t dt. Okay? And it's kind of an important one to be able to see as far as my position. Well, what happens to these things if my initial position was at 3 feet? So let's say I started at t equals 0, I was 3 feet, say, to the right. Okay, how would that change the answers that I had above? Well, regardless, if I started at 0 or I started at 3, and then I moved, what that graph shows, is that going to change the total distance I traveled? And the answer to that question is no. I'm still going to travel a total of 16 feet, regardless from where I started. Is my displacement going to be different? And the answer to that question is no. My displacement is the number of units I have moved completely in relation to where I began. My displacement, whether I start at 0 or 3, my displacement, I'm still displacing 10 feet, so that doesn't change. But does my position change? And the answer to that is yes, because my position, if I'm starting at 3, okay, that's my initial position, okay, plus my displacement, and above on that displacement on the top, notice I went 8 to the right, then I went 3 to the left, and then I went another 5 to the right. Well, where is my position at the end? Well, because I know that's going to be, I started at 3, then I had a displacement of 10, that means I'm at the 13-foot mark. Okay, so my final position is going to be 13 feet. And if I showed that as an integral, well, that's my initial position plus my integral from 0 to 5 of v of t dt. Okay, so that's kind of what we're looking at. Just remember, total distance. The total distance you move, positive and negative. We have no negative direction when we're talking total distance, or we don't want it. We want it all to be positive. Displacement is the distance you are in relation to where you began, and position is always going to be your initial position plus your displacement is going to give you the position that you're at. Well, let's cruise along here once. Well, suppose ds dt, the derivative of position with respect to time, better known as v of t, actually equal t squared minus 4t plus 3 feet per second. That's going to represent the velocity of a particle moving along the x-axis between 0 to 5 seconds. Okay? And I should have had units on there, but I don't. Now, why are we back to this horizontal particle motion? Because I guarantee you're going to have one on your AP test on May 4th. Okay? So, find when the particle is moving left and when the particle is moving to the right. So, I'm getting rid of this whole screen share. I don't want it on there. Well, in order to do that, we're going to do this two ways, okay? And we're going to do this algebraically, and we're going to do this graphically. But in order to get there, we got to think back in the beginning of the year. Find when the particle is moving to the left, when is it moving to the right, and when is it stopped on our interval from 0 to 5. Well, how do we get that? Well, remember, if things are moving to the left, v of t is less than 0 or it's negative. If it's moving to the right, v of t, or velocity, is greater than 0 or it's positive. And if it's stopped, remember, v of t actually is going to equal 0. And when I'm stopped, if my velocity went from positive to negative or negative to positive, I also changed direction, okay? So remember, velocity gives us the direction that something is moving. If it's positive, it's moving to the right. If it's negative, it's moving to the left. If it's 0, it's not moving at all. Well, there's two ways to do this. We can do this algebraically, okay? And you might have to do one of these algebraically on the AP test. But bottom line, I know V of t equals t squared minus 4t plus 3. And it may be calculator active, it may not be calculator active. Okay, so right now, algebraically, we're gonna picture that this is not calculator active. Okay, and if you find yourself going down the rabbit hole using the quadratic formula, you're going down the wrong rabbit hole. They're not going to make you do that on the AP test. It's going to be a nice factored problem. Well, remember, we want to find out when our velocity is 0. Well, this is going to be, oh, that does factor really nice. It's right, t minus 3 and t minus 1. So I know when t equals 3 and t equals 1, I'm stopped, okay? So these, oh, nice little things. This is when it stopped. And I don't know if it changed direction or not. Well, how do we know if it's moving to the right or moving to the left? Well, think back. First semester, what did we do? Well, we kind of, if you remember, we set up our number line test. And we put our 1 here. We knew velocity was 0. We put our 3 here because we knew our velocity was 0. We know the beginning of our interval started at 0 and it ended at 5. And what we were looking for was, am I positive or negative in there? And just remember, we're using our first derivative test here now to see if it's positive or negative. Oh, it's been a while since we've done that. But all we're going to do is we're going to check if it's positive and negative. Well, if I'm looking in here between 0 and 1, okay, I do not have to pick a number between 0 and 1 because 0 is not a critical value, remember. These are my critical values. That's when my derivative, that's when my velocity equals 0. So these are my critical values, of which 0 is not. So then I'm going to come up here and say, well, 0 minus 3, this is going to be a negative number, times 0 minus 1, that's going to be a negative. A negative times a negative is a positive. So I know I'm moving to the right here. And then between 1 and 3, well, now I'm going to put in a 2. And that's going to give me, here, this is going to give me a negative times a positive, which means it's a negative. So now I'm moving to the left right there. And then if I pick anything between 3 and 5, I can even pick 5 because 5 also is not a critical value. Or I could use 4. It doesn't really matter. But I'm going to put a 5 in there. That's going to give me a positive times a positive. That's going to give me a positive. So now I'm moving to the right again. And I can see maximum and minimums in there. And right off of my number line, I can say I'm moving right. I'm moving right on the interval from 0 to 1, union with 3 to 5. And I'm moving left from 1 to 3. Okay, so I'm moving right, moving left. So this is telling me the time at which my particle is moving right and moving left. Well, it's important to know when I'm moving right, when I'm moving left, to see how I'm going to find my total, do I want displacement, total distance traveled, or what? And just remember, when you're writing these intervals down here, it doesn't matter if you use parentheses or brackets. Well, that's one way to do it. Okay, if this were a calculator active test, I wouldn't expect you to be algebraically solving this thing. I would hope you are just going to come to your calculator, and I'm hoping you would just graph that function. And what I did was I graphed my x squared minus 4x plus 3. Okay. Of course, I changed the t's to x's so I could graph it. And notice my windows, I took my x window or my t from 0 to 5 because I don't want to see outside of the interval width. And I just made sure it fit in my window. So what I'm going to do is I'm going to take my tool here, and I'm going to capture that page really quick, and I'm going to paste it because you would be just simply reading this in your calculator, and you're going to take this little guy over here, and we're going to squirrel him in there, and we're going to see that this actually worked out really well. Well, on the calculator, I'm not going to waste my time to do it, but you would want to make sure that that point there and that point there, that is truly 1, 0, and that this is truly 3, 0. You can use trace, you can use menu, whatever you want to use to get in there. But see, we can see we're stopped at 1 and we're stopped at 3. Well, remember, if velocity is positive, you're moving to the right. If velocity is negative, you're moving to the left. And again, if it's positive, you're moving to the right. I can see I changed direction at 1 because I was moving to the right, then I moved to the left, then I moved to the right again. Okay, so my displacement and my total distance traveled are going to be two different numbers because I did a little backtracking here, all right? And that would be the non-algebraic way right over here. Non-algebraic way. And you're going to have those on there, okay? When is the particle moving right, left? When did it change direction? We're just going to graph our function if it's calculator active. It's fast, it's short, it's sweet, okay? Next thing we're going to do is suppose the initial position of the particle is s of 0 equals 4 feet. We're going to find the position at t equals 2 seconds, okay? Well, we're going to do this a couple different ways, okay? Remember, my position at t equals 2. My position is going to equal position, not displacement, not total distance traveled. My position is going to equal my initial position plus my integral, which, well, I'm going to say, how do I want to do this? I'm going to say plus displacement, which in the end, my position is going to equal my initial position plus my displacement, remember, is by taking the integral from a to b of v of t dt is how we're going to be able to find that. Okay, my integral is the position. So we want to be able to write an integral that represents this. It does come, okay, it does come out where you're going to be on your free response portion of the test, and I promise you, you're going to have a couple of these questions. They're going to say, write, but do not evaluate an integral representing this situation. Well, if I need to know my position, remember my position function is my s function, my position function at 2, well, that's going to equal my initial position of 4 plus my integral from 0 to 2, because I started at time 0 and I'm ending at time 2, of v of t dt. Okay? And it's really important you know how to do that. That's really writing that integral, it's a pretty big deal to be able to write what they are talking about. And then a lot of times they don't even want you to integrate it. They just want to know, do you know the calculus of it? Okay? And then other times they're going to say, hey, find it. We can find this algebraically as well. Okay, remember, our v of t on this problem, v of t, actually equaled t squared plus, or no, not plus, it was minus t squared minus 4t plus 3, I think it was, yep, plus 3. That was my velocity function. And if they want me to find my position, okay, well, up here I know s of 0 is 4 feet. So I initially started at 4. So that means what's going to happen is I can algebraically find this. My s of 2 is going to equal my initial position of 4, like I said before, plus the integral of 0 to 2 of t squared minus 4t plus 3 dt. You're going to have these too, whether or not it's calculator an active portion or not, but you're going to have these, okay? So how would we do that? Well, this is going to equal 4 plus the integral. Well, what is my displacement? Well, that's going to be my antiderivative. Remember, that's the antiderivative command. So it's going to give me 1/3 t to the third minus 2t squared plus 3t. We're going to evaluate that from 0 to 2. Well, that's going to equal 4 plus, don't forget when I evaluate these, okay, I'm going to get upper limit minus lower limit. And so I got to plug in here. So when the 2, that's my upper limit, 2 comes in, well, that's going to give me 8/3 minus 8 plus 6. And then my lower limit comes in, and that's going to be minus 0. So I know as I'm cruising and bruising here, it's going to be 4 plus, well, 8/3. What is 8/3? 8/3 is 2 2/3. I can kind of put these two together and say minus 2. And, well, that's going to give me 4 plus 2/3. And everybody knows that equals 4 2/3 feet. Okay? So that is my displacement. So bottom up, not my displacement, that's my position. So I know S, my position at 2, is going to be 4 2/3 feet, or I could call it 14/3 feet. We can find these algebraically by integrating and evaluating like we just did there, okay? We can also find this stuff in our position, or in our graph, I'm sorry. Well, what do you mean? Well, graphically, this is the first way, algebraically we did it. Now, we're going to look at it, we're going to do it graphically. Well, graphically, how do I know this? Well, if I came back here to my calculator, or I don't even have to say graphically, but what I can do is I can evaluate that integral. Let me come back here. Calculator. If I need to know what S of 2 is, well, I know it's 4 plus the integral from 0 to 2 of b of t dt. Well, I know I can do that. My calculator will evaluate that integral. Well, there's two ways to skin a cat. If I pull this up, I can evaluate this integral from 0 to 2 right in the graph page. I do not have to do it on a calculator page. Well, how do we do that? Well, we're looking at our graph, and we're just going to say menu, analyze graph, and we're going to do an integral. And it tells me lower bound, well, that's my lower limit of 0. Enter. My upper bound is going to be my upper limit of 2. And I can see that that is going to give me 0.667. Okay? Well, when I do that, I can come here and I can go Tools. I can capture that page here. So I can come back and I can say Edit. Let's paste that little bugger on here. And what I'm going to do is I'm going to pull this down here. And this tells me I can see from here what has happened is this is my accumulated area from there to there. So it's going to be 4 plus 0.667 or 4.667 feet. Please don't forget your units or they will downgrade you on your units. Well, that's one way to do it. I don't have to do it that way. I can come right back here to my calculator and I can be in a calculator page. Well, remember, when I graph this, okay, it's important to know my velocity function here, it's stored in f1 of x, so I don't have to define my function or anything like that. I can just leave it in there and come here, and I can say, well, what is 4 plus menu calculus integral from 0 to 2, and I can cheat. I don't have to type it in like they have there, the t squared minus 4t plus 3 dt, because it's defined in my calculator as f1 of x, so I might as well plug it in like that and say dx, and then if I hit enter, hey, there's the 14/3, and if you're like, hey, I don't want the 14/3, I can bring that down, and I could approximate that at 4.667. And again, I can insert, I can say tools, I can capture that little bugger, and I can come right back here, and I can think I can paste them in there right there. And I can grab this little bugger, zippity-doo down here, and I can use my calculator to get it either in the graph page or a non-graph page. Well, just so you know, there's a third way to do this, okay? What do you mean a third way? Well, let's come across here. I know the third way that I can get this is still algebraically. Well, how come? Well, I know V of t equals t squared minus 4t plus 3. And I also know my initial position at time 0 is 4. Okay, well, we can find that because if we're looking for the position at 2, we are finding what is s of 2 equal. Not really sure. But we do know that if we integrate velocity, we get position, don't we? So we know the antiderivative of v of t is s of t. And if I integrate t squared minus 4t plus 3, well, I know that's 1/3 t cubed minus 2t squared plus 3t plus my constant of integration. And I can come back here and I can use my initial condition. And I can say 4 equals 0 minus 0 plus 0 plus c. So c equals 4. Well, that's kind of slick because now that I know c is 4, I also know that my s of t function, s of t equals 1/3 t cubed minus 2t squared plus 3t plus 4, shocker, okay? And what can I do? Well, heck, if I know that, and I need to know what the heck is s of 2, well, if I have my position function, I can just plug it in. And that's going to give me 8/3 minus, is that 8? 2 squared is 4 times 2, it gives me my 8, plus my 6, plus 4. And if I collect all this, well, this is 2 and 2/3. And if I put all this business together right here, that gives me plus 2, right? 2 and 2/3 plus 2. Well, that's 4 and 2/3. Or I could call it 14/3. Or I could call it 4.667 feet. As long as I put feet on them, I am good. So bottom line, okay, I can find my position using my velocity function, okay, integrate velocity plus initial position. I can graph my velocity function. I can accumulate that area under the curve, add that area accumulation to my initial position to find the position. I can type it into my calculator, or if I'm actually given the function like they did, I can actually integrate the velocity to find the position function, okay? And then just plug the time right in there. Because this is position, okay? If I need to know the position at time 0, I plug a 0 in there. Well, look at there, I get 4. If I need to know my position at 4, I could plug a 4 in there. But I can also do all that back here too, because all I have to do, if I need to know my position at 4, that's going to be s of 4 is going to equal 4 plus the integral from 0 to 4 of v of t dt. So I can find these a couple different ways, all right? Well, where are we at? How about t equals 5? Write an expression, okay, write an expression showing v to t, the object's position at t equals 5 seconds, okay? What would you do to write an expression to show the object's position, okay? Remember, we know what v of t is. We know where it started. It still started s of 0, never changed. It was still 4. So if I need to know what my position at 5 is, for me, the fast way, the calculus way to do it is to take my initial position plus my displacement from 0 to 5 of v of t dt, and know what this means, okay? Know what this means. Okay, that it's an important concept. Know the integral, the accumulation of velocity gives you displacement, okay? And once we know that, all we got to do is come back here, because we're in the calculator, and I could just come right up here and I could scroll that down and come back and say, hey, all I need to do is change u to a 5. Shazam! I'm 32/3. And if I didn't like that, well, I could come up and I could grab that and I could say, 10.667. And I could come right down there and say, well, that means S of 5 is 32/3 feet. Or I could call it that 10 2/3 or 10.667. It really doesn't matter, okay? But the question, last question today, is find the total distance traveled by the particle over the interval 0 to 5. My total distance, totally different question. Total distance. Do I need to know where I started from to find out my total distance traveled? Okay? No, we do not need, there is no need for initial position. The initial position is only going to come into account if I'm trying to find the position of the object at a particular time. If I'm just after total distance, okay, total distance, all I need is the integral from 0 to 5, and it's total distance, so I want to take the absolute value of v of t dt, okay? And that's what I'm going to have to get. And if I came back to do that, well, that's just coming right back here, and I'm going to come up here, and I'm going to copy that little guy, and I'm going to come back over here to the side, whoa, and I'm going to say delete, delete. Now, I want the absolute value, so I can scroll in here, and I can do the old ABS parenthesis, and then it's going to absolute value that thing, and when I hit enter, it's going to give me 28/3 is going to give me my absolute value, okay? So this is going to equal 28/3 feet, okay? Or if I really want to wig it out, I can say 9 1/3 feet. I can call it 9.333 feet. As long as I round to 3 decimals, it doesn't matter which one you use. Now, algebraically here, it's a little bit different, okay? And algebraically, it's different because I'm going to get a picture of my graph on here once, and I will be right back, okay? Let me hit pause. Okay, if I didn't have a calculator to do this, I really wouldn't want to do this, and I'm not going to do it. But maybe the problem would show you this graph, and it would say, write but do not evaluate an integral, okay? Well, they wouldn't do that because then you would probably just write it this way. But if you had to algebraically calculate this total distance, okay, it's really important to know that this here is positive area, this here is going to be negative area, and then this here is going to, again, be positive area. So I would have to do this integral 3 times, because I would have to take this positive area, I would actually have to say my total distance traveled is going to be my integral from 0 to 1 of v of t dt, if I forgot about the absolute value. Now I know this is negative area here, so if I subtract negative area from 1 to 3 of v of t dt, that's going to make it positive, and add this last little bit of area from 3 to 5 of v of t dt, I would have to evaluate this integral 3 different times to get it. Well, because you know this is going to be a positive area right here, and I can see it in the graph, minus this one right here. Well, this is going to be a negative area, so if I minus a negative and then add that last, add that last positive down here because it's up there, well, minus a negative, well, that turns that into a positive, doesn't it? So it's positive plus positive plus positive, and algebraically, if I didn't have a calculator, that's what I would have to write out, and that's what I would have to evaluate, remembering v of t is t squared minus 4t plus 3. I'd have to find each one of these integrals so that I could add them together. But this right here is an important indication. Knowing its negative area, if I subtract it, it's going to turn it positive, okay? And what we're going to do from there is tomorrow we're going to accumulate some acceleration to get some stuff with velocity, okay? So have a good rest of your day.